let me discuss the existence theorem. What are the properties for a function whose Laplace transform exists? Let ft be a function defined for all t greater equal to 0. And number 1, it is piecewise continuous continuous on 0 to infinity. And it is piecewise continuous on a finite interval this, and number 2, it is of exponential order. So a function ft whose Laplace transform exists, it must satisfy two conditions. One is it is piecewise continuous and the other is it is of exponential order. If both conditions satisfy simultaneously, then Laplace transform of ft exists, and given by Laplace transform of f of t is equal to f of s, but s is positive. So the function should satisfy two conditions: piecewise continuous on a finite interval as well as is exponential order. So what does mean by exponential order? Let me have the definition of exponential order. A function ft is said to be of exponential order A if limit e minus at f of t approaches infinity exists. If a function satisfies this criteria of the limit, if you are finding the limit by something, finding like this, f of t is this and e minus at. So then if the limit is definite, then the function f of t is said to be exponential order. For example, 1 t square t raised to the power n, where n is a positive integer, sine omega t, cos omega t, sine hyperbolic at, cos hyperbolic at, EAT, they are all of exponential order. If you are putting ft here and see whether the limit exists, yes or no. If the limit exists, then the given function is of exponential order. But ET square is not of exponential order. Not of exponential order mean, if you are putting ET square there, e minus at here, and you are taking the limit, since ET square does not vanish. If you are taking the derivative, it is ET square into 2t, something like that, so it is, limit is infinity. Limit does not exist. If limit does not exist, so it is not of exponential order, and if one of the condition fail to exist, then you cannot find the Laplace transform of this function, which is not of exponential order. Let us have unit step function. Unit step function. Unit step function. It is defined as unit step function t minus a, or it is going to be Heaviside function. It is going to be 0 if t less than a, and this will be 1 if t greater equal to a, for all a greater equal to 0, a positive real number. So unit step function is purely a switch on, switch off function, and when t is less than a, there is any real number, so it is off. At t is equal to a, you just switch on and it is going to be take the value 1 and it is going to be 1 afterward. Suppose this is t and here unit step t minus a on y-axis. So this is a real number on t-axis. If t less than a, this is going to be 0. Once at t is equal to a, you just on it, it is going to be a jump of 1 unit. This is a jump of 1 unit and it will attain the value 1 afterward unless otherwise you switch it off. So a is a real number and this is the definition. If I am going to have t plus 5, so it is invalid. Because if I am writing this in terms of minus 5, look at that. So my a is greater equal to 0. So this is the right format for defining a unit step function where a is a positive real number. And there is minus there. Laplace transform of unit step function. Let us find Laplace transform by definition. This is e minus st unit step t minus a dt by definition. And it is very interesting to note it down whenever you are going to have unit step function in the integral sign. If it is going to appear in the integral sign, you are going to interpret at splitting up the two length of the interval. 0 to infinity can be split as 0 to a plus a to infinity. And this is e minus st unit step t minus a dt or e minus st unit step t minus a dt. So you have split up according to the unit step. If suppose this is 10, for example, if this is 10, so you are going to 0 to 10 and 10 to infinity. If it is something like that, like it's a. Now the definite integral, the limits are written 0 to a here because t is the variable of integration. Here t is written a to infinity, upper lower limit. The lower upper limit, this is the lower upper. Now as t is less than a, what is going with the unit step function? This is going to be 0. Look at that. If t is less than a, unit step is 0. So this is 0. Since t is less than a, so this vanish. Here t is, look at this inequality. T is greater than a. If t is greater than a, unit step value is 1. It means this is going to be 1 now. Laplace transform of unit step function is going to be a to infinity e minus st into 1 dt. Look at that. This is 0 and the whole integral vanish, and here this is 1. So it is going to be like this. Let me integrate. This is minus 1 over s e minus st a to infinity. Minus 1 over s is there. E minus infinity e minus as. T is the variable of integration. T is replaced by infinity and then t is replaced by a. Minus 1 over s here, this is 0. E minus infinity is 1 over infinity, which is 0 minus as. So if I multiply this minus, so I will get e minus as. So Laplace transform of unit step function is 1 over s e minus as. Pulse function. We have defined the unit step function like switch on, switch off. Now we are defining the pulse function. Let a and b are real numbers. A and b are real numbers with a less than b. This is the condition. Because you can have a equal to b, a less than b, a greater than b. So these are the properties of two real numbers. They can equal, one is less than, the other is less than, something like that. If two real number a and b with a is less than b, define a pulse. Define a pulse which is of the form ut minus a minus b. This is the pulse function. This is the pulse function you are having. So if I sketch this pulse function, let me sketch this pulse function. I have this something unit step, I am going to this t less than a greater equal to 0, t less than b equal to a, t greater equal to b. So there are two unit steps involved because there are two numbers a and b. When a is less than b, you have defined a pulse like this. And if you're sketching, how would you sketch? You have to start less than a and then greater equal to a less than b, then greater equal to b. If t less than a and obviously a is less than b, that is 0. That is 0. T less than a, according to unit step, it is 0. And since a is less than this, if it is 0, that is 0. Now coming to this step, t is less than b. If t less than b, this is 0, according to the definition of unit step function. But here t greater than equal to a, it is 1. It is 1. Next, t is greater equal to b. If t is greater equal to b, it is 1. But since a is less than b, it is 1 as well. Look at it. Because b is greater than a. Here b is greater than a. If t is greater than b, it is greater than a. It means 1 minus 1 is 0. This is going to be 0 again. So let me sketch the pulse, which is this is a, this is b, and there is t. So there is a pulse function on y-axis. Less than a, it is 0. A and b, if t lies between a and b, it is 1. Look at that. 1. And greater equal to b, it is 0 again. Look. So this is a pulse you are getting when two real number, one is smaller than the other. And this is important fact in solving a couple of questions. When you are writing in terms of pulse, then you have to find Laplace transform. This is the pattern. Second shifting theorem. Second shifting theorem. We had first shifting theorem. First shifting theorem states that if exponential is multiplied with the function, so you are finding the Laplace of a function and s is replaced by s minus a. This is first shifting theorem we had. Now we introduce the unit step function. If Laplace transform of f of t is f of s, this you know. A couple of function t square, sine omega t, whatever it is, couple of function whose Laplace you know, then Laplace transform of the shifted function is f of s e minus as. That is, I am writing Laplace transform t minus a unit step t minus a is equal to f of s e minus as. This is the definition of a second shifting theorem. Because of the unit step function, the function shift itself where it is on. If it is on at a, the function switch to there. And the Laplace for finding the function, and do not forget to put e minus as with it. Because of the unit step function shift itself where it is on. So we have discussed unit step function, Laplace transform unit step function, pulse function, as well as the second shifting theorem. This is the second shifting theorem we are having. Now a few examples. Sketch the function number number 1. So the question consists of 3 steps. You have to sketch the function which are assumed to be 0 outside the given interval. Outside the given interval. This is first step. You have a question you are solving now using unit step function and finding the second shifting theorem something. First of all, you have to sketch the function which lies in the interval, and after that it is going to be 0, which is assumed to be 0 outside the given interval. This is first step. Write in terms of pulse. Pulse function. Write in terms of pulse function, hence find its Laplace transform, because find its Laplace transform. This first question is of 3 steps. The first one is t, and t lies between 0 to 2, for example. A function t is given and that lies between 0 to 2. Let me sketch. This is t, this is 2, this is 0, and here f of t. When t is 0, it is 0. When t is 2, it is 2. Since a linear function, you were having this. You look at that. And it is going to be 0. It is going to be 0 outside the interval. In the given interval 0 to 2, it's t. This is t. This is first step. Writing in terms of pulse. So, f of t is equal to t. Value of the function is written outside the bracket. And since these 0 is less than 2, I have written the pulse, then a is less than b. Since 0 is less than 2, I am writing t minus 0 minus 2. This is the way I have defining the pulse. This is the unit step function. Look at that. T minus 0 minus t minus 2. This is. Now here t is the value of the function. F of t is equal to t. Unit step t minus 0 minus t. Unit step t minus 2. The value which I have written outside, it is going to be multiplied with each unit step. Look at that. Now I have to take Laplace transform. Since a unit step function is there, this t must be t minus 2. So first of all, I am going to have t minus 0 minus, let me t minus 2. If I am going to have t minus 2 there, I should add 2. I should add. And unit step t minus 2. Look at that. If I am going to make t minus 2, I have to add that. So this is t minus 0, unit step t minus 0 minus. This something a, this something b. Both are multiplied with the unit step function. So it is t minus 2, unit step t minus 2, and this minus is multiplied with plus. It becomes minus 2 times unit steps t minus 2. Now this is ready for the Laplace transform to be taken. Not at this stage. Not at this stage. Here you are making t minus 2 and then you are adding something. And then after this step, taking Laplace transform now. So the left hand become a function of s, because the small letter are obviously the function of t and the capital letter are the Laplace transform, which is a function of s. Here if you are finding the Laplace transform using second shifting theorem, let me write the second shifting theorem again so that you will understand. F of s, e minus as. This is the second shifting theorem I have written. So here t is a function. What is the Laplace transform of t? 1 over s square e minus 0s. Because a is 0 there. 0s. Minus t is a function. T is a function. The Laplace is 1 over s square e minus 2s because a is 2 here minus 2 Laplace transform of unit step function 1 over s e minus 2s. So this is the Laplace transform of a function that lasted in interval 0 to 2 and afterward it is 0. You have sketch and write in pulse and then you let me have a few more so that you will understand. Sin pi t, another function where t lies between 1 and 2. This is the function lies in that interval and after that it is going to be 0. Let me sketch the function again. So this is t, here's your f of t and this is 1, this is 2. When t is 1, sin pi is 0. When t is 2, sin 2 pi is 0. Let me have 3 by 2 there. 1.5. If you are unable to this function, find the function, let you shorten the interval. So let you are going to take any point in between 2 and 1. So 1 and 2 it is 1.5 which is 3 by 2. If you are putting t is 3 by 2, so sin 3 pi by 2 is minus 1. Minus 1. Here minus 1. So the function is going to be this and it is going to be 0. It is going to be 0. Look at it. So sin pi t is this function which is assumed to be 0 after, before and after that interval 1 to 2. Let me write in terms of pulse. Sin pi t outside. 1 is less than 2. I am writing t minus 1, t minus 2. This I have written. Sin pi t unit step t minus 1 minus sin pi t unit step t minus 2. This I have. Before taking the Laplace transform, since it is unit step function, so it should be t minus 1 or it should be t minus 2. So let me arrange it. Pi outside t minus 1 plus 1. Unit step t minus 1 minus sin pi, I am making t minus 2. T minus 2 plus 2. Because if I subtract, I add. In order for the equation to be balanced, u t minus 2. Look at that. Now think carefully. This is your A and this is your B. Now pi is there. Pi is multiplied with it. Let me have the trigonometric identity. Sine of A cos of B. Cos of B means cos of pi. A pi is multiplied. Cos pi is minus 1. So it becomes minus sin pi t minus 1 unit step t minus 1. Sine of A cos of B plus cos of A sine of B. And when sin pi it is 0. The other half is 0 of the trigonometric identity. First half is there. Let me have again here. This is A and this is B. Sine of A cos of B. Cos of B means 2 is multiplied with pi. Cos 2 pi. Cos 2 pi is 1. So minus is as it is. Sin pi t minus 2 unit step t minus 2. The other half of the trigonometric function identity will vanish. Now this is ready for the Laplace transform to be taken. It is going to be like the unit step function. Look at that. T minus A. Taking Laplace transform. This is f of s is equal to, here minus as it is, sin pi t is a function. Sin pi t is a function. So it is pi s square plus pi square. The Laplace transform minus s. A is 1. Minus pi over s square plus pi square e minus 2s. A is 2. Laplace transform of sine pi t is pi over s square plus pi square. So this is the function whose Laplace transform you are finding. Write down the function, sketch, assume to be 0 outside, write in terms of pulse, then the function is multiplied. And make sure you are going to arrange like this. If you are subtracting, you are adding something. And something like that you can do it. T minus 3, t is greater than 3. This is 3, this is 0, 1, 2, this is f of t, and this is t. If t is greater than 3, it is this. It means if I am putting t is 3, it is 0. 3, 3, 0 and 4, 5, 6. It means if t is greater than 3, let me have t is 4. If t is 4 and 5, this is 4 and 5. 3 plus 0 and 4 bit is 1, 5 bit is 2 and something like that. Look at that. So let me have, it is a straight line like this. Straight line like this, I have a bubble on 3. There is a bubble on 3 because I am not taking 3 in this. It should be greater than 3. But if I am taking that, that's a bubble. So it means I have to start with 4. When I have t is 4, it is 1. When t is 5, it is 2 and so on and so forth. And before t, it is going to be 0. This is the function. So I am writing t minus 3 unit step t minus 3. This is a wonderful idea. If there is only 1, you are writing t greater than t unit step t minus 3 for one value. If t greater than 3, it is this. If t less than 3, it is 0. Obviously, the definition of unit step function is this. If t less than 3, it is 0. And if t greater or equal to 3, it is this remaining. So, if you have one value, not all 2, because the previous 2 question we have t lies between 1 and 2, 0 and 2. Here t is the single. It should be bigger than 3. So, value the function there and you are writing unit step t minus 3. So, it is going to be ready for the Laplace transform to be taken because no need to add or subtract. It is already t minus 3 units. Oh, look at that. So, t is the function whose Laplace you have to find, which is 1 over s square e minus 3s. Because a is 3 this time. So, e minus 3s you have to put it down. We have second shifting theorem with us. Let us have the inverse Laplace transform. For example, if I am writing 1 over s square, a function. Suppose I am writing this function and I said find its Laplace inverse. Your answer will be t. If a function is t, whose Laplace inverse is 1 over s square. If I am writing another time 1 over s minus 2 whole square. Let me write this. And I said find its Laplace transform. Your answer will be, this is t, 1 over s square is t, and since s is shifted to s minus 2, you have to 2t there. Look at that. First shifting. Since s is shifted, after that 1 over s square is t, and you have to multiply with exponential, which is e to t. Now the next step is, if 1 over s square e minus 2s. Look at that. If this is a function, for example, and I said find its Laplace transform, look at the second shifting theorem. Once you are finding the Laplace transform, it means this is because of unit step function and this function whose Laplace inverse you have to find, which is t. But this time t is shifted to t minus 2, unit step t minus 2. This. I mean, you have to switch this from your side, t minus 2, unit step t minus 2. Laplace inverse of this function is this. And if you are finding its Laplace, you are getting this thing back. Because if you are finding Laplace of this, Laplace of t is 1 over s square and e minus as is 2. So, Now we have seen the simple function whose Laplace inverse we have found, and then when s is shifted, and then when exponential something like this. A few example more.